Hello everyone, I'm Alka Jangir from IIT Kanpur. Welcome to the course Basics of Materials Engineering. Today we'll be talking about thermal processing and heat treatment of steels, continuing from previous week. So this course is offered by Professor Ratnakumar from Department of Mechanical Engineering, IIT Madras. And firstly we'll be going through some sample assignment questions, then we'll be going through some lecture notes which will be helping you in solving your assignments. So in first question, you are asked the microstructure of steel cool down rapidly from 800 degrees Celsius to 500 degrees Celsius and held there for 1 second, followed by rapid cooling to 50 degrees Celsius. So what can be your possible microstructure? So your options are 50% pro-eutectoid ferrite plus 25% bainite plus 25% martensite, or 50% bainite, 50% martensite, 50% pro-eutectoid cementite plus 25% bainite and 25% martensite, or 50% pro-eutectoid cementite plus 50% bainite. Now your answer will be 50% bainite, 50% martensite. So this you have to draw a cooling curve in this your isothermal transformation diagram, so which can be done like this. So you are rapidly cooling from 800 to 500, so rapid cooling won't change your any microstructure. It will be austenite. Here it will be metastable because it is below eutectoid temperature. So on sudden cooling up to 500 degrees Celsius, your austenite will transform into metastable austenite. So after this, you are holding this for 1 second. So this metastable austenite will transform here up to in bainite, and this will be only completed to 50% as it is touching this 50% line. So there will be 50% bainite transformation and 50% metastable austenite. Then on sudden cooling up to 50 degrees Celsius, which is below MS temperature as shown here, so that will be convert your remaining 50% austenite to the martensite. So your final structure will be 50% bainite and 50% martensite. Now this 50% bainite won't change on and rapidly cooling below this bainite temperature because it is a stable structure. Second question. In this question, you are asked the process rapid cool to 250 degrees Celsius, hold for 10 to the power 3 second, then quench to room temperature, results in. So you have to use the same isothermal diagram. So in this diagram, you first have to rapidly cool up to 250 degrees Celsius, then hold, then quench. So you have to tell what will be your microstructure: 100% martensite, 100% upper bainite, 100% lower bainite, or bainite plus martensite. So your answer will be 100% martensite. And this will be your cooling curve. So you will be rapidly cooling it up to 250 degrees Celsius, then holding it to 10 to the power 3 seconds. So we can see that up to this point, on sudden cooling up to 250, your austenite transforms into metastable austenite, and on holding it for 1000 seconds, this metastable austenite remains the same as it does not encounter any transformation line. Then on sudden cooling, your metastable austenite transforms into martensite. So there will be 100% martensite in this case. In third question, The process rapidly cool to 750 degrees Celsius, hold for 500 degrees Celsius and hold for 500 seconds, then quench to room temperature. Results in your options are cementite plus perlite, or cementite plus martensite, or perlite plus martensite. So again you will have to draw a cooling curve and determine what will be the microstructure. So answer will be cementite plus martensite, and this will be your cooling curve. So firstly you are cooling it rapidly up to 775 degrees Celsius, then holding for 500 seconds. So this isothermal transformation will be leading to formation of proeutectoid cementite. On holding it for 500 seconds at 775 degrees Celsius, your partial austenite will be transforming into proeutectoid cementite, and remaining metastable austenite, it will be quenched, then it is entering into ms temperature, so it will convert into martensite. Then on sudden cooling, the remaining metastable austenite transforms to martensite, and cementite being the stable phase, it remains the same. So your final structure is cementite plus martensite. Next question is the process rapidly cool to 700 degrees Celsius, hold at temperature for 10 to the power 5 second, then quench to room temperature. Results in your options are perlite, so your options are perlite, proeutectoid cementite plus perlite plus martensite, or proeutectoid cementite plus bainite plus martensite, or proeutectoid cementite plus perlite. So again you have to draw a cooling curve based on the conditions that are given. So in this case you are cooling it up to 700 degrees Celsius, then isothermally transforming your material up to 10 to the power 5 seconds. So up to that point you have to keep it isothermally at constant temperature, then you have to rapidly quench. So we can see that here your cementite will form in this area, then perlite is forming, and so their complete transformation is occurring because it is going up to green line. So it will be consisting of proeutectoid cementite plus perlite. So on sudden cooling up to 700 degrees Celsius, your austenite will transform into metastable austenite, and on holding for 10 to the power 5 seconds, this metastable austenite will transform into proeutectoid cementite plus perlite, and on sudden cooling, this proeutectoid cementite and perlite will remain same, as these are the stable phases. Now the process rapidly cool to 400 degrees Celsius and hold for 500 seconds, then quench to room temperature. Results in your options are cementite, bainite, perlite, bainite plus martensite. So again answer will be bainite. (500 seconds) you are holding, so okay, 500 will be more than 100, so it will be complete bainitic structure. So on sudden cooling up to 400 degrees Celsius, your austenite will transform into metastable austenite, and on holding it for 500 seconds, this metastable austenite will transform into bainite, and then on sudden cooling, your bainite remains the same, as this is stable phase. Next question is based on continuous cooling transformation curve, and previous ones were related to a TTT curve or your isothermal transformation curve. So you had to hold your steel at particular temperature. Here you are continuously cooling. So in this curve, you can see there is bainite formation, there is austenite to ferrite transformation and austenite to pearlite transformation. So there will be various mixtures of formations. So in the first question, you are asked the microstructural constituents of the alloy obtained with a cooling rate of 10 degrees Celsius per second. Your options are martensite, martensite plus bainite, and martensite plus ferrite plus bainite, or martensite, ferrite, bainite and pearlite. So in this case, you have to draw a continuous cooling curve for a particular cooling rate. So in this case, answer will be martensite. So this will be your cooling curve faster than 8.3 degrees Celsius. So it will be a little left to this curve. So this is not going through either ferrite transformation or bainite transformation, and at this nose relates to your critical cooling. So from the graph we can see that the critical cooling rate is 8.3 degrees Celsius per second, and here 10 degrees Celsius per second is cooling rate is applied. And when cooling rate is higher than critical cooling rate, then complete martensite is formed. Now next question is the microstructural constituents of an alloy obtained with a cooling rate of 0.1 degree Celsius per second. Now in this case you will be having your curve in between 0.3 degrees Celsius per second and 0.03 degrees Celsius per second. So your curve will be in between these two curves. So we can see that this curve is going from austenite to ferrite transformation, but it is not going up to finish line. So there will be some ferrite formation here, and then remaining austenite will be quenched and forming martensite. So there will be formation of your, and also it is going through bainite initial line as well. So there will be formation of martensite, ferrite and bainite. So as written here. So from this graph we can see that critical cooling rate is 8.3 degrees Celsius, but we are applying a cooling rate which is very less compared to that. So there won't be complete martensite won't be forming. This cooling curve is coming from ferrite and bainite regions. So along with martensite, ferrite and bainite will also form, and the cooling curve isn't crossing the entire transformation curve. So martensite will also form. So if this curve will go from this area where it will be going through finish line, then complete pearlite will be forming, complete ferrite will be forming, and won't be forming any martensite. In this question, the microstructural constituents of alloy obtained with a cooling rate of 0.1 degree Celsius per second. Your options are martensite, martensite plus bainite, martensite, ferrite, bainite, martensite, ferrite, bainite and pearlite. So 1 degree Celsius per second will be in between your 8.3 and 0.3 degree Celsius per second. So it will be in between this, and in this your microstructure is given as martensite and bainite because it is crossing only bainite transformation region. So from this graph we can see it is your cooling rate is lower than critical cooling rate. So martensite will form along with your bainite as well. So this cooling curve enters the bainite transformation region but does not encounter the bainite finish line. So the remaining metastable austenite transforms into martensite. So the final structure will be bainite plus martensite. The microstructural constituent of alloy obtained with a cooling rate of 0.01 degree Celsius. So in this case, your curve will be in between 0.0 degrees Celsius per second and 0.006 degrees Celsius per second. So in between this curve will fall, and in this region we can see that it is coming from austenite to ferrite, austenite to pearlite, austenite to bainite. All these three regions, along with there will be martensite forming. So all four phases will be forming in this case. So all these four structures will be forming in 0.001 degree Celsius per second. Now, an annealed 0.3% carbon steel contains approximately 30% perlite and 70% ferrite, and the approximate tensile strength of the alloy is blank kpsi. So your answer will be 64, and for this your formula is given in the notes. So approximate tensile strength for a hypoeutectoid steel depends on percentage of ferrite and percentage of perlite. So if you have to just multiply 40,000 times the percentage of ferrite plus 120,000 times the perlite percentage perlite divided by 100. So in this case, as you are given your 0.3% carbon steel which contains 30% perlite and 70% ferrite. So you can multiply 40,000 times 0.7 plus 120,000 times 0.3. So it will give 28,000 plus 36,000, which will give you 64,000 psi. And in kilo psi you can divide by 1000, so it will be 64k psi. Now we'll be going through some lecture notes. So firstly, in previous lecture we talked about TTT curves, how they are plotted using various cooling curves, isothermal cooling curves. So based on that, now we'll be seeing the TTT curve for hypereutectoid steel. So in this case, you'll be having a proeutectoid phase will be forming in one region of the curve. So for iron carbon alloys of other compositions such as hyper or hypoeutectoid steels, a proeutectoid phase will be existing. In previous lecture we only saw for eutectoid steel the TTT curve for eutectoid steel. Here it is for in case of hyper or hypoeutectoid steel. So there will be this curve will be separated by austenite to cementite transformation, austenite to ferrite transformation initially, then it will be moving into austenite to pearlite transformation. So hence there should be another curve describing that reaction, and this figure shows isothermal transformation diagram for an hypereutectoid steel for 1.13 weight% of carbon, which forms a proeutectoid cementite phase. So this reaction will also take place above eutectoid temperature. So this line is extending further beyond eutectoid temperature. This is TTT diagram for 4340 steel. So this steel will be consisting some alloying elements. So that's why in this case there can be bainite formation as well. So there will be different bay for austenite to ferrite transformation, austenite to pearlite transformation, and also for austenite to bainite transformation. And then there will be MS, martensite start and martensite 50% and martensite 90%. So this all depends on these MS, these depend on temperature. So these don't depend on time, they are not time dependent transformations. Now there are various cooling curves drawn for this isothermal transformation diagram. So with using different cooling curves you can obtain various microstructures, and depending on that your final steel product will have different properties. So for example, cooling curve 1 is, this is x1, x dash 1. So in this case, you're cooling very slowly your steel. So this type of cooling curve is similar to annealing. So in annealing, you know that there will be coarse perlite that will be forming and it will be having very low hardness. So your transformation will begin at x1. Before that, it is not encountering the transformation line, so there will be metastable austenite. Now at x1, transformation will start and it will keep on, your percentage of perlite will keep on increasing as you are moving further. So it will be completed at x dash 1. It is similar to annealing and it forms coarse perlite. There is a slight change in size of perlite that forms at beginning to the end because there is slight change in temperature. So temperature is changing, so your size of perlite will also change. The transform product is relatively soft, which has Rockwell hardness 15, and after x1 dash the sample may be cooled down to room temperature rapidly as there will be no further transformation. Cooling curve 2, in this case you are cooling this isothermally at lower temperature. So at lower temperature what happens, you have a certain super cooling, so your transformation will complete before to previous cooling curve. So transformation begins at x2 and finishes at x2 dash. It describes isothermal annealing. In isothermal annealing, you cool below the critical temperature at isothermal. So you cool at, you keep it at a single temperature. So it leads to very uniform perlite formation, uniform size perlite formation in your steel. So it has uniform coarse perlite microstructure and hardness, and the transformation finishes at much shorter time scale than case 1. In case of case 3, in this case you will be forming medium perlite. So it is much faster cooling rate than the annealing. So it is typical of normalizing, and your transformation starts as x3 and completes at x3 dash, and this indicates formation of coarse perlite in much shorter time than annealing. It finishes at x3 dash forming medium perlite, and the large temperature difference between x3 and x3 dash, so structure shows greater variation in fineness of perlite. There will be smaller portion of coarse perlite than annealed samples. Cooling curve 4, it shows formation of fine perlite having very high hardness, which is Rockwell hardness 40 at C scale. Now much faster cooling rate than normalizing in case of slow oil quenching. So microstructure will be a mixture of medium and fine perlite, and your transformation starts at x4 and finishes at x4 dash. In case of your cooling curve 5, in this case it is typical of intermediate cooling rate. So in this case you are only transforming partial perlite. So in this case, typical of intermediate cooling rate, it starts transforming to fine perlite at x5 in relatively short time, and your transformation to fine perlite continues until curve becomes tangent to some percentage transformed. Here 25% at x5 dash, and below this curve the cooling curve is going in the direction of decreasing percentage transformed, and transformation stops with further cooling until it hits, after it comes out of this transformation line, it will stop forming perlite, and the remaining metastable austenite will convert into martensite. So the microstructure will be 25% fine perlite and 75% of martensite. in cooling curve 6 to 7, 6 and 7, these are both have cooling rate. 7 has equal to critical cooling rate, so this will also form complete martensite, and 6 has higher cooling rate compared to critical cooling rate, so this will also form complete martensite. So it remains austenitic until MS and then transforms to martensite. It has 100% martensite, which has very high hardness. The cooling curve 7 is the critical cooling rate, below which there will be either pearlite or bainite transformation. Now cooling curve 8, in this case you are isothermally cooling below nose temperature. So you are rapidly cooling up to bringing this curve below nose temperature, and then isothermally cooling it for converting it into lower or upper bainite. Now cooling rate is similar to 6, but at 8 we hold at constant temperature. This starts to transform into bainite, and in order to form complete bainite, cool at faster rate to miss the nose and then hold it at constant temperature for sufficiently longer time. So this will give you lower bainite having Rockwell hardness around 60. Your martensite will have Rockwell hardness around 65. Now up till now we have seen the isothermal cooling. So here cooling will be done at the constant temperature. Now we'll be doing cooling with continuous cooling. So with continuous cooling, what will happen? You're plotting these types of continuous cooling plots. Now in this curve, what is happening compared to isothermal cooling? We were quenching and holding it at a higher time at a lower temperature. So just holding at lower temperature was providing it super cooling that was required. In this case, you are not providing much super cooling, so these curves are shifted to the right and below to the your isothermal diagrams. So these curves will be relatively right on the right side, and in case of plain carbon steels, this will be only up to nose temperature, and below that you can't form bainite by continuous cooling. Now isothermal diagram can't be used when the cooling is done continuously, and the diagram must be modified for transformations that occur as the temperature is constantly changing. And for continuous cooling, the time required for a reaction to begin and end is delayed. So this diagram is called continuous cooling transformation or CCT type of diagrams. In this case, MS and MF line occurs at a same temperature for IT and CCT diagrams. So as we know, this is not time dependent. These type martensitic transformations, these lines remain the same, and this curve will be little bit shifted to the right and to the lower compared to your isothermal diagrams. Now two cooling rates are shown here. One is slow, one is fast in CCT diagram. So with the slow cooling rate, this one, it will lead to formation of coarse pearlite. So transformation is occurring in between these transformation lines, and for fast cooling rate it will form fine pearlite, and if you cool it much faster, it can only form with the critical rate, it will form complete martensite, and below that it will form fine pearlite. So there won't be any bainite transformation. In continuous cooling, bainite is not formed as the transformation to pearlite would have finished before it reaches the bainite temperature. Hence the diagram doesn't have lower nose region, and the transformation terminates along this AB curve. Microstructure and cooling rates. Now these are the two extreme cooling rates that are shown. So with this rate you will be getting your 100% perlite. If you increase you decrease your cooling rate in this side, then you will be getting only perlite, and if you increase above this and between critical cooling rate, then you will be getting martensite plus perlite. And if it is kept higher than this critical cooling rate, you will be getting 100% martensite. So this will be specific characteristic of the cooling curve, this critical cooling rate. Now CCT diagram for an alloy steel. In case of alloy steel, you are adding some alloying elements which will help you in formation of bainite as well. So here a bainitic line will also be there, and your martensite formation will be easier compared to plain carbon steel. So carbon and other alloying elements, they shift the perlite and bainite noses to the longer times, thus decreasing the critical cooling rate. And bainite formation is possible for non-eutectoid plain carbon steels. And the CCT diagram shown is for 4340 steel. Now this diagram I have already explained this in various questions. So with different cooling grades, you will be getting these different microstructures. So it can be martensite, mixture of martensite bainite, martensite ferrite bainite, martensite ferrite perlite bainite, or ferrite and perlite. Now we'll be reading about heat treatment. So heat treatment is your combination of heating and cooling operations timed and applied to a metal or alloy in a solid state in a way that will produce desired properties. So basic heat treatment of steel involves transformation or decomposition of austenite. And final properties, physical and mechanical, of treated steel, it depends on the nature and form of transformation products. Now the first step will be heat the steel above a critical temperature to form austenite. So these all heat treatments, most of them, they have to do with your eutectoid transformation. So rate of heating to the desired temperature is not important in many cases, but it is in case of highly stressed material due to cold working or welding or other reasons, they should be heated slowly compared to stress-free steels to avoid distortion. The practical rule is heating to be done as slow as possible to avoid any ill effects. First heat treatment is annealing. In case of annealing, material is exposed to elevated temperature for a very long time, then they are cooled very slowly, and this annealing is carried out to relieve stresses. So in case of stress relieving annealing, in this case we heat your steel product to temperature below lower critical temperature. So this will lead to some diffusion in your material, leading to relief in stresses. Second is increased softness, ductility and toughness. So after annealing, you will be getting quartz perlite. So that material will show you higher ductility and toughness. It also produces a specific microstructure if you want to convert your certain microstructure. So that then you will be using annealing. So for example, in case of spheroidizing annealing, you want to make your cementite in spheroid form, then you will be using this annealing. A variety of annealing heat treatments are possible. characterized by the changes induced in the microstructure and mechanical properties. These are the steps that are used in annealing. So in step 1, first heat your steel at a particular heating rate to a desired temperature. So this temperature can be below lower critical temperature as well. In some annealings it can be above lower critical temperature, or it can also be above upper critical temperature. So it is held here for some time, which is known as hold time or soak time. So holding or soaking at that temperature, then cooling down to room temperature. This holding is done so that the temperature reaches at a particular temperature uniformly throughout the specimen, and then cooling down to room temperature. Now this cooling can be with different cooling grades. So if it is in this case I think this plot is okay. So if it is very high cooling rate, then it will be quenching. Below that it will be normalizing, then it will be annealing. This plot is not plotted correctly. So the time is an important parameter in these processes due to thermal gradients that exist in the interior and exterior of the material. Fe3C diagram in the heat treatment temperature range. Now what are the various holding temperatures that I used? These are for normalizing. It should be above upper critical temperatures, and for full annealing, in case of hypereutectoid region, it is just above lower critical temperature. So in case of A1 is your lower critical temperature, A3 is your upper critical temperature. So these are various annealing processes. First is full annealing. In that case you will be heating it above this lower critical temperature. And spherodizing, in this case it will be heated up to higher temperature for spherodizing your cementite. Stress relief, it will be below lower critical temperature, so just to relieve the stresses. Process annealing will also be below lower critical temperature. Normalizing will be having different cooling rate compared to annealing. First is full annealing. So this is for hypoeutectoid steels. In this case, heat the steel to proper temperature and then cool slowly through the transformation region in the furnace. So annealing is also said as furnace cooling, and normalizing is air cooling. So in hardening, you quench the material with using various mediums, which can be oil quenching, it can be water quenching, depending on what cooling rate you require. So the purpose of annealing is to refine the grain, induce softness, improve electrical or magnetic properties, and to improve machinability. This is very slow cooling process, hence close to iron carbide equilibrium diagram. So the microstructure that will be forming here it can be seen in your iron carbon diagram. Heat treat a coarse grained 0.2% carbon steel to refine the grain size. So for this, firstly there will be no change in microstructure occurs during heating. Firstly, we are heating steel from room temperature. So first, up to when you take your steel up to above A1, then you will start seeing some change in microstructure. So up to A1 there will be no change in microstructure, and at A1 perlite area will transform to small grains of austenite through eutectoid reaction, and the original large ferrite grains, they remain the same. If we cool from this temperature, grain refinement doesn't happen because ferrite is already existing. So only the area that has converted into austenite, only that will change. So continued heating between A1 and A3 allows the large ferrite grains to transform to small austenite grains. Now we cool up to this temperature, then all above A3 entire microstructure will be small grains of austenite. Then subsequent furnace cooling results in, after we have achieved this structure, then it is subsequently cooled. So there will be formation of pearlite and ferrite grains. So it results in small grains of pro-eutectoid ferrite and small areas of coarse lamellar pearlite. And the proper annealing temperature for hypoeutectoid steel is 500 degree Fahrenheit above A3 line. Full annealing in case of hypereutectoid steels. Refinement of grain size for hypereutectoid steel occurs at 500 degree Fahrenheit above lower critical temperature. And heating above this temperature will coarsen the austenitic grains, which on cooling will transform to large pearlitic areas. And the microstructures of annealed hypereutectoid steel will consist of coarse lamellar pearlite areas surrounded by a network of pro-eutectoid cementite work. And the excessive cementite network is brittle and tends to be a plane of weakness. Hence, annealing should not be the final heat treatment process for hypereutectoid steels, and presence of thick, hard grain boundary will also result in poor machinability. Now, this formula, as I told in previous question, 10th question, so this is approximate tensile strength of annealed hypoeutectoid steels that may be determined by the proportion of ferrite and pearlite present. So there is fixed hardness of ferrite and pearlite. So this hardness, this is multiplied by their fractions. So with multiplying the fraction and adding that will give you tensile strength of your steel. For example, in an annealed 0.2% carbon steel, which contains approximately 25% pearlite and 75% ferrite, whose approximate tensile strength is 40,000 times 0.75 plus 120,000 times 0.25. So it will give you 60,000 psi. So this same formula can be applied to hypereutectoid steel since their strength is determined by continuous cementite network. Now next is ferrodizing annealing. In this case, annealed hypereutectoid steels have poor machinability due to the microstructure which has pearlite plus cementite network, and since cementite is hard, the cutting tool can't cut through these plates, and the spherodizing produces a spheroidal or globular form of carbide in ferritic matrix, which is shown here. So these are the cementite spheroids in the matrix of ferrite. Now prolonged time at elevated temperature will completely break up the pearlitic structure and cementite network. Now cementite becomes spherical, which is the equilibrium geometric shape. Now one of the methods for spherodizing, now these are three methods that is used for spherodizing annealing. So it can be either prolonged holding at a temperature just below A1, or it can be heated and cooled alternatively between temperatures that are just above and below A1, or it can be heated to a temperature above A1 and then cooling very slowly in the furnace, or holding at a temperature just below A1. Spheroidized structures is desirable when minimum hardness, maximum ductility or maximum machinability is important. In case of low carbon steels, They are seldom spheroidized for machining, because in this case you will be having very less size of these, less number of these cementites, because it has low carbon. So in case of low carbon, we avoid this. We compare to medium and high carbon steels, this is used. So low carbon steels are seldom spheroidized for machining, as in the spheroidized condition they are excessively soft and the cutting tool tends to push the material rather than cutting it. And too long exposure to spheroidized annealing temperature leads to coalescence of cementite particles to form elongated structures, which in turn leads to reduced machinability. Spheroidite, this is the structure which is found in spheroidized your steels. So spheroidite forms when the pearlite or magnetic steel is heated and held at a temperature below eutectoid for a sufficiently long time. For example, at 700 degrees Celsius, which is lower than eutectoid temperature, for 18 to 24 hours. In this case, Fe3 phase appears as sphere-like particles embedded in a continuous ferrite matrix. This transformation happens by additional carbon diffusion with no change in compositions or relative amounts of ferrite and cementite phases. And in this case, a two-phase microstructure consisting of spheroidized scarpite and ferrite, which is formed by heat treating pearlite, bainite or martensite at a temperature below the eutectoid temperature. Stress relief annealing. Now in this case, you are heating your steel below A1 temperature and holding it for a particular time and then cooling in furnace. So stress relieving is a heat treatment process which helps to remove internal stresses caused to the metal when it is machined, cast, rolled or forged. It is typically involves placing the metal into a set temperature for a certain amount of time. Then the metal is cooled using a controlled method, and the stress relieving must be done carefully to remove stresses, because if you are cooling it at a higher rate, then it might again introduce some stresses in the metal and without impacting the metal's properties that should be kept for the part. So this treatment can be done for both ferrous and non-ferrous metals. Other process, annealing. So in this case, steel is heated below the critical temperature, keep it at that temperature for a while, then cooled slowly. It is also called subcritical annealing. It is suitable for low carbon steels. Phase transformation not involved in this process, and the material is in the same phase in throughout the process, and the process annealing is cheaper than full annealing. So it is used in sheet metal and wire industries. Normalizing is carried out by heating steel to 1000 degree Fahrenheit above A3 upper critical temperature, followed by cooling in still air to room temperature. Its purpose is to produce harder and stronger steel than full annealing, and for hypereutectoid steels it is necessary to heat above ACM line in order to dissolve the cementite network. And normalizing may also be used to improve machinability, modify and refine cast dendritic structures, refine the grain, and to homogenize the grain structure. The increase in cooling rate due to air cooling as compared to furnace cooling affects the transformation of austenite and the resultant microstructure. So as cementite is dissolved in this case, So cementite is dissolved in this case because it is a non-equilibrium type of cooling in case of normalizing. So more carbon can be dissolved in your perlite. So there can be a case where there won't be any cementite formation even in your hyper-eutectoid composition. Iron-iron carbide equilibrium can't be used to predict the proportions of pro-eutectoid ferrite and perlite or pro-eutectoid cementite and perlite, as the cooling is not done under equilibrium conditions. There is less time for formation of pro-eutectoid constituents. Hence, there will be less pro-eutectoid ferrite in normalized hypo-eutectoid steels and less pro-eutectoid cementite in hyper-eutectoid steels, because formation of these phases, it will require diffusion. So while in case of normalizing, you are cooling faster. In hyper-eutectoid steels, sometimes the cementite network may be absent altogether. Hence, normalizing increases the strength of hyper-eutectoid steels. Normalizing also affects the temperature of austenite transformation and the fineness of perlite, and the faster cooling rates, they lead to lower temperature of austenite transformation and finer perlite. Now the difference in spacing between cementite plates and perlite is shown for annealing and normalizing. So now in this case, annealing, there will be this size of the cementite plate as well as distance between them will be higher. So this will be coarse lamellar type of structure in case of annealed steels. In case of normalizing, there will be fine perlite. So the thickness of perlite as well as the distance between them will be lower. Now this steel will give you higher toughness. The cementite plates will be closer together in case of normalized medium perlite, and they tend to stiffen ferrite, so it will not yield easily, thus increasing its hardness. Normalizing produces finer and more abundant perlite structure than that of annealing, which results in harder and stronger steel. Now next process is hardening. In this case, under slow or moderate cooling rates, the carbon atoms are able to diffuse out of the austenite structure. The iron atoms then moves slightly to become BCC. From FCC to BCC transformation will be there, and the gamma to alpha transformation takes place by a process of nucleation and growth and is time dependent. With increase in cooling rate, there is less time for carbon to diffuse out of solid solution. Although some movement of iron atoms takes place, the structure cannot become BCC while the carbon is trapped in the solution. And the resultant structure called martensite is a supersaturated solid solution of carbon trapped in a body-centered tetragonal structure. The structure will look like this. Now these are the BCT type of structure. It is tetragonal. It has C and A. So there will be some C by A ratio. In case of BCC, these C and A will be equal. So this carbon is trapped here in octahedral voids. In hardening, the two dimensions of the unit cell are equal, and the third dimension is elongated because of trapped carbon, and the axial ratio C by A increases with increase in carbon content to a maximum of 1.08. This highly distorted lattice structure is the prime reason for the high hardness of martensite. Atoms of martensite are less densely packed than austenite, and hence an expansion occurs during transformation. This expansion produces high localized stresses, resulting in the matrix's plastic deformation. After drastic cooling, this martensite appears microscopically as a white needle-like acicular structure, often described as pile of straw. Now this is your iron carbide diagram. In this case, from austenite to conversion into low temperature phases. So this cooling can be at different rates. So if you are cooling it slowly, then it will convert into pearlite plus pro-eutectoid phases. This can be cementite or ferrite, and it can be, if moderate cooling is there or air cooling, then it can form into bainite or fine pearlite. If it is rapid quenching, then it will form into martensite. So the transformation is diffusionless and there is no change in chemical composition in case of martensite transformation. There will be small volumes of austenite suddenly changes its crystal structure, and the transformation proceeds only during cooling and ceases if cooling is interrupted. Hence, the transformation depends only on the decrease in temperature and is dependent on time only. The no, it is independent of time and depends on temperature. So the transformation of the above type is called a thermal, in contrast to one that will occur at a constant temperature. Okay, that is last slide. So if you have any query, you can ask.
Ma'am, what is the relation between thermal conductivity and temperature?
Thermal
Thermal
con-
conductivity K.
there isn't any. Why will be there be any relation in thermal conductivity and temperature? So you can say like temperature gradient will be there. Like if you are taking certain thickness of your metal, then at one side what is the temperature, at other side what is the temperature, that will depend on thermal conductivity. So if you are trying to heat your material or cool your material, if it is insulator, then there will be large gradient in temperature at both sides. So that's why you use foams and foams or various insulator clothing to help yourself in winter, or you use refractory which is also insulator to prevent heating of your room compared to your furnace. So temperature gradient will depend on your thermal conductivity.
Ma'am, actually the question is like a copper specimen is heated and they were asking like whether the thermal conductivity will be increasing or decreasing.
Based on what? Thermal conduct
A copper is heated and then they are asking like what will happen to thermal conductivity, whether it increases or decreases.
with temperature, with increasing temperature, what will be with, okay, so thermal conductivity, it's not in this current assignment, right, which is not submitted yet. Francis?
Yes, ma'am.
Yeah, it's not in current assignment, is it?
No, it was actually a previous question.
Okay, then
Uh,
its answer is already given, right? So, see, at higher temperature, what will happen? Your bonds, your atoms are easy to vibrate at higher temperature, right? Compared to at lower temperature. So, if it is easier to move, then your thermal conductivity comes from your uh, vibration of these phonons and atoms. So, it will be higher at higher temperature, according to me.
okay, ma'am. Ma'am, actually, they are giving the answer as decreasing. The copper has fairly higher thermal conductivity at room temperature. This is because the larger number of valence electrons which are free to move in the lattice. Thus, electrical conductivity will decrease with the temperature.
That
This
is
is like the
that is electrical conductivity. Thermal conductivity is also decreasing at higher temperature. That's what you are saying.
yes. The, the, for the thermal conductivity also, is it like this?
Yeah, it is. Yeah, it is also given. Yeah, on net it is given that at higher temperature, your movement of free electrons is restricted, so your thermal conductivity will also decrease at higher temperatures, similarly to your electrical conductivity.
So actually, this thermal conductivity is related to the valence electron.
Yeah, free electrons. Yeah.
So if actually if the temperature is increasing, the movement of this valence electron will be increasing, isn't it? So why is it actually decreasing?
No, free electrons. It your thermal conductivity will depend on two things, right? Your electron movement as well as your phonon interaction. So in case of like insulators where you don't have free electrons, there it is dominated by these phonons, these bonds. So in case of, for example, in diamond, when you talk, there is no free electron, then it is dominated by phonons. So in case of this, your metals, you already have free electrons. So at high temperature, it is restricted the movement. So that's why it will increase at high, it will decrease at higher temperature, similar to your electrical conductivity.
Okay, ma'am. Uh,
Okay.
ma'am, actually, in the previous lecture, the you are saying like the fillet will cause the stress concentration. Actually, fillet will be reducing the stress concentration, isn't it? Fillet,
What which can what will be reducing?
the stress concentration.
Stress concentration depending on what? Which length?
Uh, I mean, the question is what doesn't act as a notch, and the options are groove, smooth
Yeah.
contour, hole, and fillet.
Yeah.
Actually, the fillet will be reducing the stress concentrations in it.
Yeah, but compared to
Only the smooth contour is,
a material which doesn't have fillet and which has fillet.
yes. The smooth contour and also this fillet should be the answer, isn't it?
Smooth contour meaning it has like, in case of a material which doesn't have any fillet and it has fillet. So if it has holes in terms of rounded corner, then it will be having like, compared to square corner, you will be preferring fillet type of rounded corners. But if you have a smooth contour that you are forming, then it will be having less stress concentration. Smooth contour, if there is also present, then I think that should be answer compared to fillet.
Ma'am, if it is a multiple choice, then multiple correct option, then can we give that fillet option?
Then yes, yeah, fillet can also be given.
Okay. Ma'am, what do you mean by this homogeneous deformation? I mean, the word homogeneous means it will be same in a particular direction. So it was asking that necking portion, whether the deformation is homogeneous or not.
After necking, it is not homogeneous. Like up to, for example, up to necking, what you see, you are seeing the your, in case of gauge length, it will be, your length will be changing homogeneously in entire length. But as soon as you start forming neck, then there will be localized formation of one, like it will be change in cross section, abrupt change. So if a neck has formed, after that it won't be homogeneous. Your trace will be concentrated in that region. So there will be triaxial type of stress concentration there. So it won't be homogeneous after necking.
That means the direction of deformation will be different along the having different direction. Before that, it will be only along the tensile stress direction. I mean the tensile force direction deformation.
Yeah, your deformation will be equally spread in the entire gauge length before that, before formation of necking. After necking, it will be restricted. Your strain will be more in your the localized region where your necking has occurred.
Okay.
Okay.
Ma'am, in the heat treatment, it will be actually changing the phase and grain boundaries, isn't it? So it should be affecting the elastic modulus.
No, if using like elastic modulus, you can't change much using heat treatment. Like it mainly depends on composition of your steel. It doesn't affect much if you are changing your heat treatment. Elastic modulus is not very sensitive to heat treatment.
So if a question is like whether we can change the elastic modulus, then do we need to pick that option, or we can
Heat treatment, elastic modulus is not sensitive to your heat treatment. So I don't think you should check that mark. It mainly, like if you're changing into martensite and perlite, then there will be main change will be in your tensile strength and yield strength, fracture strength. It won't be changing, and ductility will change, toughness will change, but elastic modulus pretty much remains same. It is only for changing elastic modulus you require, for example, formation of composite, or changing in composition. If you are changing amount of carbon to very large extent, or changing, adding nickel or other constituents.
okay. And another one is actually for a given material, impact energy will be seen to decrease in the yield energy increase. Actually, when we increase the yield strength, the area of the graph is actually increasing, isn't it? So it should be the impact energy should be also increasing, isn't it?
Can repeat? I didn't understand properly. If you are changing yield strength,
Uh, for a given material, the impact energy will be seen to decrease if the yield strength is increased.
yeah.
This is actually the statement. When we are increasing the yield strength, actually the area of the graph is increasing, isn't it? I mean, the slope is increasing to a higher point, and will be getting more area, isn't it? So it should be the impact energy is actually the energy absorbed under the graph, isn't it?
No, impact energy is different. Impact toughness is different than your toughness that you measure using graph. In graph, how you measure your graph? See, when you measure your tensile graph, then you apply the loading rate, your strain rate is very slow. In case of impact toughness, you apply the strain rate that is very high. So in that case, it depends on yield strength of material. If yield strength is very high for a material, then it acts as brittle material. So it won't absorb much energy. So it will break very fast. So it will have low impact strength, impact toughness, if it is higher yield strength. That toughness is different from your toughness that you measure using very low strain rates.
So if the yield strength is higher, then the toughness will be lower.
Toughness you have to define, like if it is impact toughness, then how it if you're talking about impact toughness, then it will be inversely proportional to your yield strength. If your yield strength is higher, then impact toughness will be lower. If you are talking in terms of like in your graph, your tensile testing graph, in that case, if you have impact toughness higher, then if you have yield strength higher. So in case of your stress strain curve, engineering stress strain curve, in that case you get toughness by mainly if you have higher ductility as well as higher strength. So there should be optimum combination of both of these. It should also have higher toughness and higher ductility as well as higher strength, tensile strength. Then you'll be having higher toughness.
Ma'am, you're actually saying about the in real case, the it will be by experimentally it will be low. This impact strength will be inversely proportional to the yield strength, and by graphically we will be getting uh,
In
in a real
graph,
strength.
when you are getting graph, that you are getting by using very low strain rate. So when you apply uniaxial tensile testing, then you are getting that toughness is different from your impact toughness.
Okay, in the during that Charpy notch test, like in that kind of test, it will be sudden impact and the strain rate will be very higher.
Yes.
Okay. Ma'am, during this hardness testing, is the formulas for each hardness test is it actually important, or we only need to learn that diamond type shape and those kind of things? Uh, the each kind of formula is it that really important?
Which formula are you talking, like?
I mean, for the Brunel hardness, there will be a formula, isn't it? And for Vickers test, and there are different kinds of formula for each test,
Yeah.
isn't it?
Yeah, they're mainly Brinell hardness formula is not that hard, right? P upon it's in terms of load and diameter. Brinell formula you can remember, and Vickers formula you can remember. These and Rockwell is also easy enough. So two three formulas you can remember because question might be asked in exam. You just write it
Okay.
down on paper, and if you see it multiple times 2 3 days, then you'll remember. These are I think simple enough.
Ma'am, will be getting any kind of question like there is a rebound test isn't it for the uh, so for some other kind of test. So that kind of do we need to learn any formulas in it for that?
Shore and poultry, I think, have sir taught it in lecture. If sir has covered, then he might give question. I think whatever sir has taught, try to like go through it.
Okay. Ma'am, and there was another slide like fracture mechanics. The failure occur when the stress plus crack geometry is greater than the material fracture toughness. And for strength of material, the stress is greater than material strength. By meaning the strength of material, we terming that about the beams and those things. So if it is greater than the yield strength, then it will be a failure.
In case of fracture mechanics, you are considering that there is certain existing certain defects are already existing. In case of when you are talking about like strain stress strain engineering curve, then you are assuming that your material is defect free. Then you are getting particular tensile strength, then you assume that only up to going by that particular tensile strength or fracture strength, then your material will fail. But when you talk in terms of fracture mechanics, then you are assuming that there is porosity or some other defects are already existing. That's why that fracture toughness will that fracture that you are getting, those will be lower compared to what you get using these either theories or the engineering stress strain curve. Because the machine components that you'll be using in real life, they will always will be having certain defects in them.
So in the fracture mechanics, we will be considering that crack geometry and everything.
Yeah, in certain fracture mechanics, then you consider that there might be already pre-existing defects. So you also assume like what can be the critical size of that crack, or all those you consider.
Now, in the homogeneous and heterogeneous phase systems, there was an example of that sugar and liquid, isn't it? In that case, the liquid plus solid sugar means it is actually homogeneous or heterogeneous. Actually, both the composition are same, isn't it? But they are in different phases. So they will be considering as heterogeneous phase.
Okay, up to solubility. Like there will be some particular solubility for the water. So if you're have sugar in solvent or up to solubility, if it is in form of solution, then it will be homogeneous, right? So it will be like ferrite. If you're considering in case of ferrite, you have carbon percent in solubility limit, so that will be your single homogeneous system. So it will be heterogeneous when you are adding more sugar, then it can dissolve. So in that case you will be also finding some sugar that will be in solid form, then it will be heterogeneous.
So if it is having different phase than present, then we can say solid phase precipitated. Then we can say it will be in heterogeneous state.
Yeah, they'll
Um,
yeah.
Ma'am, so in that two phase region, then it will be heterogeneous. I mean, alpha plus Fe3C. alpha plus gamma, like that region, the phases will be heterogeneous.
Yes.
Ma'am, but by meaning chemically homogeneous means only they should have same chemical formula. Is like,
In case of, okay, homogeneous meaning at every point you'll be finding it in terms of chemical formula or microstructure. It should be all should be equal at all regions.
ma'am, and in that Gibbs rule, there is a formula split: P plus C equal to F plus. Actually, in some places it's given value number like one or two.
Okay, one or two for what?
I
C
mean, for
plus.
the pure substance and everything, we will be using that plus one, and in some other cases, we are using actually plus two.
Okay, plus 2 meaning you can change either pressure or temperature. In case when you are drawing your iron carbon diagram or these diagrams, which are these diagrams that you are plotting, these are your considering pressure to be 1 atmosphere. So in that case, you are just you can only vary temperature. So you are taking plus 1 in that case. You are taking plus 2 in case of water, where you are at one axis you are taking pressure, at one axis you are taking temperature, so you can vary both of those.
Ma'am, that will be actually degrees of freedom, isn't it? F is you're saying about the F value, isn't it?
No, the last part, that what you are using, right? Degree plus f, degree of freedom will be equal to f plus p will be equal to c minus
I
2,
mean,
c plus 2.
yes, ma'am. In the right hand side, we will be,
So
but
plus 2 defines whether you can change two things or one thing. So 2 will be when you can change both pressure and temperature. If you can only change temperature, then it will be 1. In case of mainly these diagrams that we use, composition temperature diagrams, for binary diagrams, then you use 1, because you are considering pressure to be constant.
ma'am, can you explain that source and sink of dislocation? What do you mean by source and sink of dislocation?
Source meaning how they'll be generated, and sink meaning they'll be going there and will be part of that particular thing. So for example, your grain boundaries are mainly called source and sink of dislocations. So your grain boundary areas, they don't have a crystalline structure, right? So they can be generated from there, the dislocation, and they can be go there and become part of a grain boundary. So they won't be counted as grain boundary then. So how many, if you are measuring the density of dislocation in your material, then you are measuring how many dislocations are there per inch square or like that. Then if you are applying particular plastic deformation on a material, then a dislocation can generate from grain boundary, and it can go and go into the sink as well, become a part of grain boundary.
Okay, ma'am. But actually, in that slide, it was given like grain boundary. It is not actually the reason for the hardness and enhancement in the metal. Actually, if the gray size of the grain boundaries will be affecting this hardness, isn't it?
What is given?
Like a grain boundary also act as a source and sink of dislocation, but that's not the reason for hardness enhancement in metals.
Yeah, no, in that case, what was given, like you had to find out what is the reason for hardness or something like that. So it was a statement that wasn't a reason for the question, or like that. Like the question, that part is correct, that statement is correct, but it didn't relate to what was the question. What was the question? Can you repeat the question? You have.
The question is in the whole pitch model, hardness increases with the reduction in a grain size because grain boundaries
Yeah.
options are given like act as source of dislocation, act as barrier to the dislocation, act as sink of dislocation, act as dislocation motion.
Yeah, so answer will be barrier to dislocation, because if dislocation motion what leads to plasticity in metal. So grain boundaries, what they do, they restrict the motion of dislocation from one part of the grain to the other part. So it can't move from one grain to other grain easily. So if this is restricted, then there will become a pile up of dislocations. So this pile up will lead to increase in strength of material. So that's why hall paste relation comes into picture. But if it is acting, your grain boundaries are also act as sink and your source of dislocation, but it isn't the reason of the question.
Okay. Ma'am, in that metastable state, the statement was actually given. The no, it is actually a non-equilibrium state, but with very long time for changes to occur. When we take that Martensite is actually a metastable state, isn't it?
Yeah.
So in that case, even if we are keeping it too long, the we'll be having that Martensite, isn't it? The Martensite is actually not changing to any other phases.
No, but compared to iron carbide, cementite, compared to that, it is highly metastable. Because if you are heating it up to 50 degrees Celsius or something, then it might convert into other, like for example, when you provide some heat treatment, tempering. In that case, you heat your steel up to 200 degrees Celsius or something like that. Then it can change your martensite to benite or other phases. So compared to that, cementite and graphite, when you compare those two, compared to that, it is less metastable, your cementite phase. For that, you have to heat it to very high temperature to very long time to convert your cementite into graphite and ferrite.
Slowly cooled, its cemented decomposes. By
Sorry.
meaning the like in the Greek as Aeon, it is written like when the molten cast iron is slowly cooled,
Hmm.
it cementate decomposes.
Decompose.
Actually, cementate means Fe3C. In which region the cementate will be decomposing?
In which region? Okay,
The
so
cementate.
if you have no, it's related to like what you told, right? Why we call iron carbide diagram a equilibrium diagram? Because when you if you leave your cementite to very high temperature for very long time, then it will break into your graphite and ferrite, because graphite is more equilibrium phase compared to cementite. Cementite is Fe3C, so it is an intermediate compound compared to your graphite, which is highly stable equilibrium phase compared to cementite.
So that graphite formation is actually termed as here the decomposition.
Iron carbon diagram is different, so in that case you'll be forming when you cool your liquid iron carbon, so that will cool and forms graphite. So there will be all these reactions as well. Your in case of cast irons you get different these reaction based on iron carbon diagram compared to iron cementite diagram. In white cast iron diagram, you will be forming cementite, but in case of grey cast iron, where you will be forming graphite, that will follow the iron carbon diagram.
Okay, ma'am. Ma'am, in that Hume-Rothery rule, actually the first rule is given like the greater the difference in the size between solute and solvent atom, lower the solubility limit. But if the size of the atom is higher, then uh, the other solute atom can easily get into the voids of that solvent, isn't it? So it should be it should be increasing, isn't it?
No, in case of Hume-Rothery, what you want 100% solid solubility. So for 100% solid solubility, it is mainly seen in substitutional solid solutions. So for example, copper nickel system, right? There are other options as well, like other in these case you can see 100% solid solubility isomorphous type of structure. But if you are adding these small interstitial atoms, then there is chances of formation of intermediate compounds. So these compounds will form, then there won't be any solubility, 100% solubility, because of formation of these compounds. So that's
So
how
it's actually due to that size difference. It's actually
it
this.
should be like very less. If there are two atoms sitting very side by side in periodic table, they are more likely to form isomorphous system.
The point about that electronegativity difference is higher. Is it actually decreasing due to the formation of compound?
Electronegativity is reducing.
I mean, greater the electronegativity difference, the solubility will be lower. It's actually the statement
Yes.
for the Hume. So
Yes.
if the solubility is getting lower, since when the electronegativity difference is higher, then they will likely form compound instead of so
Yeah.
is that the reason?
Instead of forming this, yeah, solid solution. So solid solution is more likely to show a isomorphous type of system. If you have already formed like Fe3C type of compounds, Fe3C or other Cu3Ni or these type of like intermetallics if you form, then it is less likely to be a solid solution, complete solid solution up to 100% of another element. So there should be least difference between the electronegativity.
Okay, ma'am. It will be the same case for that if the valency number is higher.
Valency number, yeah.
I mean the this common formation will be the reason.
Yeah, valency should be either equivalent, or it also, like in some cases it is shown like if it is lesser then it is more likely to, but it should be very near to each other. It shouldn't be very high difference.
Ma'am, the crystal structure resemblance, why it is actually having the crystal structure resemblance. I mean, the if it is having one crystal structure, then if the void is more for that structure, if the same thing is for the solute also, then how it can affect that solubility.
No, similarly, as I told earlier, right? So, as you were telling, like there's formation of void or something. So, as soon as you are start talking about like there will be void and another interstitial can come. So, we are not talking interstitial here. We are talking substitutional type of structure. So, substitutional meaning there will be another element atom will coming and sitting at others place. So that will be more easier if, for
Okay.
example, copper is also FCC, nickel is also FCC. So nickel will sit at copper's place and both has an FCC, then it will be easier if there is even 50-50% of both of them present.
Okay, so the solubility is mainly termed using that substitution. We won't be considering the uh, interstitial
Interstitial is not seen. Interstitial, there is not any example of interstitial type of solubility which is reaching up to 100%. But in case of substitutional, there are various phase diagrams that show 100% solid solubility. So that's what they are trying to see, because there is not much change in the energy as well. Energy is going down, so it is more stable rather than forming some compounds which is
okay.
changing the energy.
Ma'am, can you briefly explain that cooling curves to phase diagram? Like we will be drawing how we will be drawing that phase diagram from cooling curves for that the binary phase alloy. I mean, there was a temperature for the cooling curve. The T1 and T2 is actually given in a slanted position, and when we are returning that composition temperature graph, it's actually given in the straight line.
Okay, so where it is changing, like you, various cooling curves you will be drawing for different compositions. So if you are drawing for particular composition, you will be seeing when there will be phase change, there will be particular slope will be there. So particular slope, then change, then it can be constant. So if you are seeing that type of change, then you will be drawing your transformation lines on that particular composition. So now if you're matching all those lines, then you'll be getting your transformation curves. So you can just simply go and see your eutectic type of diagram. Those are simplest ones rather than going to iron carbon diagram first.
Ma'am, actually, the temperature, the both those temperatures should be actually same, isn't it? They are getting different due to the different TA and TBA. I mean, there are two components. Is that the reason they are having a slanted T1 and T2?
Okay, so it will be constant only in case of pure metal or where it is eutectic type of composition. Eutectic type of composition has a fixed ratio of or metallic compound is forming. For that particular point will also be having a constant temperature. Other than that, you are getting phase field, right? So there will be ferrite, there will be liquid, so there will be two phases, so there will be a slope will be there. It won't be at constant temperature.
Okay. Thank you, ma'am. That's all.
Okay, next week also I have summary session from 2 for 2 hours, so you can join then if you have any queries. Okay,
Same day,
same, yeah,
Saturday.
same time, yeah, same time, same
Okay.
day. Okay,
Okay, ma'am. Thank you,
okay,
ma'am.
okay.